We just showed that if you put too much steel in a reinforced concrete beam, you make the concrete the weak link in the beam. And when the concrete fails, it'll be a sudden failure. To make sure that doesn't happen, you limit amount of steel so that the strain in the steel exceeds or equals 0.005 at failure. Next, we're going to talk about the minimum amount of steel. Putting too much steel will make it brittle because you make the concrete the weak link. Putting too little steel will also make the reinforced concrete beam brittle. Let's talk about why. Before we do that, I want to talk about an analogy. So you come up to a bridge and it has a sign that says 150 pounds is all this bridge can hold. You're not sure how much you weigh. You think, oh, I might be 145, I might be 155. And so to be safe, you tie a safety rope to a pole, and the rope can hold 149 pounds. Now, can you see this doesn't make any sense, right? That doesn't make any sense because if you break the beam, that meant, right? So if this breaks, and you're falling through, help, that means you weighed more than 150 pounds, right? To break the beam. If the rope can only hold 149, that doesn't make any sense because if you break the beam, you're definitely going to break the rope. Okay? You need to have the rope be stronger than 150 and hopefully stronger than your weight. So here we go. It's very similar in a concrete beam. It takes a certain amount of moment to crack a beam open like an egg. Okay, so you're going to crack the concrete on the bottom. That's going to be called the cracking moment. Okay, let's say it's 150 foot kips to crack a beam open. I'm going to teach you probably next class how to calculate the strength of a beam with steel in it. That's going to be called MN. So after you crack the beam, you engage the steel and you calculate the strength. And so what happens in this kind of beam, uh, the beam cracks, you get some kind of compression there, tension here, and you'll learn how to calculate the moment. So if the moment with the steel is only 149 foot kips, that doesn't make any sense because once you crack the beam, the steel won't be able to hold the moment because 149 is less than 150. Just like this, if you crack the beam, that meant you weighed more than 150, that 149-pound rope is going to break as well. If you crack the beam, you had a moment of at least 150. And so with the steel, it's like the safety rope, only 149. That's not going to work. If you crack the beam, you'll rupture the steel. So you have to have more than that amount of steel. So if you have more than the minimum, this will not happen because MN is greater than M crack. Now, I'm going to skip the derivation, but all you can read it in the book. You get M crack from My over I, set that equal to the rupture strength, 7.5 square root F prime C. You get Mn, and make sure Mn is greater than M crack, and this is what you get. This is the minimum amount of steel. If you have rho greater than both of these things, okay, the cracking the beam and then instantly cracking the steel will not happen. Okay, so this is the minimum amount of steel. Okay, so again, if you have too little steel, when you crack the beam, the steel won't hold it and it'll be a brittle failure. Okay, finally, I want to end with this, the life of a reinforced concrete beam. And if you plot moment over here versus curvature, okay, which I just explained in a previous slide, it's 1 over the radius of the curve, or it's equal to the slope of your strain diagram. Anyway, you load the beam up. Okay, so you go like this. Let me use a highlighter. So you're loading the beam up. It's elastic until you get to that cracking moment. So when you crack it, I cracked. You did this homework. Well, I don't know if you checked. That I crack that you did for homework 2 is much less than BH cubed over 12. And so the moment of inertia reduces once it's cracked. And so the deflection increases, or the curvature will increase with no increase in moment. And then it keeps going back up linear, but with a lower slope. It's less stiff because E is low. I mean, the moment of inertia, is less now because it's cracked. And so notice that this slope is a lot less than that slope because it's cracked. Eventually, you get to the point where it's not linear anymore, and it's just slightly curved. And then, because you've designed it with less steel than the maximum, it's now going to yield after the concrete is cracked. And but before the compressive concrete explodes, and it's going to yield, and it's going to deflect. Okay, you get to the peak concrete stress. Things are starting to go bad, but in real life, so the stress strain curve of steel, we assume looks like this, but in real life, it looks like this. It does get stronger again and break. So it will start to increase moment strength because the steel is getting stronger from strain hardening. And then it goes and goes and goes and goes until finally the concrete strain at the top equals 003, and it dies. Okay, so that is what happens to a reinforced concrete beam that has steel greater than the minimum or less than the maximum. This is how it behaves.